adaptiveness. What else? The conditional expectation. So conditional expectation as a random variable. So expected value of y condition not less. Because we're going to say given y such that expected value or absolute value of y is finite. The conditional expectation of y condition not x is a random variable such that the following hold. What was that? Condition 1. I need to have this random variable is adapted to x by the above definition. And the second, so let me call, I guess I want to call it to be y star here. Okay, so here's the base y star. What else I have? For all event, for all x here, I have the expected value of y times indicated function of 1 by x is the same as the expected value of y star times 1 by x. Okay. So we already know from previous lecture that that conditional expectation is uniquely determined. Okay. So, all right. And it satisfies those properties that I wrote in the lecture note. Okay. So let me move on to section 5.2 on Martingale. Okay. Given, start off with the definition number 1. Given a sequence of random variable. So that's alright, given a sequence of random variable, I said a sequence, I guess, of random variables. A sequence of random variables x of n is called a martingale with respect to xn. Okay, the following is hold. Assume well, I guess. Okay, so let me do this. So for all expected value of mn, absolute value is finite. 2, I have mn is adapted with respect to the collection of random variables x n, x naught, n naught. Of course, by the above definition, being adapted here, well, means, nevertheless, let's say for all events like denoted by a sub v to be a collection of x n is a little x n, x naught is a little x naught, and n naught is a little n naught. Okay. We have mn condition on a v is a constant, right? now the third piece, the third condition is following. For n, I have expected value of mn plus 1. Condition none, as not and not. This conditional expectation is equal to so given the information of past up to x of n, your best guess of the n plus 1 is simply the x of n. Okay. We will walk through the example in a moment. For now, let me put a remark here. So note that note that the condition for 1 plus 2 plus 3 is equivalent to 1 plus 2 plus equation 5.24 in the textbook. Let me double check it up here. 5.4 on that. Equation 5.4. Alright. In textbook. Then like this equation 5.4 says for all such event AV, all right, for such event AV, we have expected value of mn plus 1 minus mn. Condition of AV is 0. So if you think, thinking about a conditional expectation as a random variable may be too abstract, then you can think about it this way as well. In other words, if I tell you any trajectory AV, so running from x0 and not up to x of n, then this conditional expectation is just 0. To see this, let's see, so from condition 3 implying 5.4. So how do we get that? So that is to go from 3 to 5.4. I just have to invoke, I believe, well, I believe I have this. Okay, so since we have the conditional expectation of n plus 1 condition on x and not x not and not is equal to n of n, we have a property that what I have for all such events AV expected value of and then plus 1 condition on So I guess let's start this. AB is equal to ln 1AB. However, this is just the same thing as condition 1AB and multiply with the probability of AB something like, and then condition 1AB probability of AB. So canceling the probability of AB on both sides, we get what we need here. So to round it up, condition of AB, same as condition of A. Okay. But that is actually an equivalent, I would say, equivalent statement, because I guess if I start from here, I can go backwards. Right? And so that would imply this. However, based depending on the situation, depending on situations, verifying condition 3. Maybe easier than calculating and reversing, right? So depending on the cases, maybe if I want to prove a martingale, then checking the condition 3 could be easier than checking the condition 504, and reversely, maybe 504 turned out to be easier than condition 3. That does depend on the situations. All right. So let me move to example to illustrate the terminology. Example. The first one is a random walk. Random walk. What does that mean? So suppose I have xn is a sequence of Bernoulli, or maybe it doesn't have to be Bernoulli, it just could be anything. Suppose xn ID with, of course, assuming expected value and absolute value is finite, with the mean is mu, right? Let me denote by x of n to be the summation of the xi. Of course, with the convention S0 is just 0. Okay. All right. Then we're going to denote by m sub n to be just n minus n times mu. Okay. Then either you can fit with S of n or X of n. Well, I guess it's good. To see this, we have to check. Of course, we have to verify a couple of properties. I need to verify 1, 2, and either 3 or 5.4. Okay, so either 3 or 5.4. I go with the number 3. So condition 1 is clear. 1, right? Expected value of mn. Well, absolute value. This is expected value of Sn plus n times mu. It's clear. And well, this is just this less than summation of expected value of xi I from 1 to n plus n mu, which is finite. Right? Here I'm using a triangle inequality, so not really difficult, I guess. Okay. So anyway, so typically condition 1 and 2 are pretty straightforward. Pretty just a routine computation. It shouldn't be difficult. Okay, where do I want to keep? I forgot. I guess I want to keep. I want to keep that. Okay, I want to keep these two as well. Also to relate back. Okay, now condition 2. I need to show mn is adapted. In other words, given any such trajectory, I have to show that mn is a constant. But that is clear because suppose given any such trajectory, xn will be xn, x naught is x naught, and then indeed n naught is just a 0, I guess. But anyway, let me just write this for the sake of notation. So given this, right, then obviously Sn is the summation of the new Sk, obviously. K from 1 to n, then m sub n is the summation of Sk minus n mu, which is a constant. And mn is adapted. This back to set. Right? So if I tell you information of the past, then the present has to be a constant, basically. Okay. I'm sorry, I should say, it's not that complicated. Alright, so condition 1 and 2 are pretty routine. Now 3. I would go with the condition 3 above here. So I have expected value of mn plus 1 conditioned on the xn dot x naught and naught. Okay, so first thing is I'm going to rewrite the mn plus 1 using that formula. Namely, that is Sn plus 1 minus n plus 1 times mu, conditioned on this. And then I will go one step further to somehow have the x of n to show up. So if notice that this is just the same thing as saying x n plus 1 plus I guess I want to go with what? Sn here minus maybe do this. Xn plus 1 plus Sn minus n mu. Maybe that is better. Because Sx plus 1, right, the sum of the xi item value plus 1, so it can be split into this. Yeah. And so by the linear property, this can be split further as xn plus 1 minus mu, conditioned on past, plus the value of, but that is just mn here. Right. So this is the linear, right? Linear property. Linear property. Okay. So now we know that m sub n is adapted to the past. So conditioning on the past, this quantity, this random variable is itself. Okay. This is independent of the xn, right? So this is independent of everything here. So the first one is simply the value of xn plus 1 minus mu. And the second term now is just as this is because xn plus 1 minus mu independent of this collection. Whereas mn is adapted to that collection. I believe that comes from a theorem that I mentioned in the lecture 5.1. I believe, let's see which one is that. So this is property number 4. This is property 4 in the theorem according to my lecture. Section 5.1, and the second piece is what is it here? Property 5. Consequent, this is just 0. So 0 plus done. Okay. Let me move on to another one. Now suppose I have, so Sn is a Markov chain. Suppose okay, so suppose Sn now is a with the transition matrix P net f of Sn. to p x y and then f y and plus this is the summation for y. Okay. Then let me denote my m sub n to be f. Is a Martin gap with respect to
Does f need to be finite?
I guess so. Well,
For converted?
maybe let's just take S to be a finite. Take a finite state space for the sake of illustration. But I guess we have to impose further condition in order to guarantee the condition one. But here maybe let's just take here let's assume S is finite. Okay, let's assume that. And so condition one is straightforward. So let's just not worry about it. And condition two is clear too, because if I tell you xn, then you know n sub n. Condition one and two, just pretty straightforward. Now to verify the last important property. Here, let's go with the equation 5.4. That would be easier. Why don't you guys try for a moment? See. Let's just try to verify the equation 5.4 in the meantime. Okay. See this? Well, I guess it's let me work out here. So we want to verify equation 5.4. Okay. Namely, I want to show. I want to show that n+1 condition on AB is expected value of n condition on AB. So what is this? This is expected value of f of xn+1 plus 1. Condition of AB, that means xn is 10, x0 is log, and n0 is a little n. Okay. Right.
now by the golf property, basically I don't need to condition on the present, correct? I guess over here, I guess, I still have M naught here. So maybe let me assume M naught is a constant, I guess, because it doesn't really make any sense starting from this point. Well, I guess the same thing because this is just M naught is just X naught. Right? So let me write this again. X naught is X naught, and M naught is just basically according to this. That is f of X naught, 0 here, right? Which is just a constant anyway, depending on the real X naught, so it doesn't really matter. So anyway, so this by my graph property, I already forget everything keeping this. So that is f of X n plus 1, condition of X n equals this is a graph property. And now, well, based on the definition of conditional expectation, that is just how I go to the next step. So that was just what what is that here? So that is the summation of the probability x of n going to all of y, and then have f times y and n plus 1. Correct? Y, yes. Right? And based on my definition of the function f, that is f evaluated at xn f. That is the definition of the function little f. Right, so this is the definition of little f. So then, well, that is what? That is simply the same thing as expected value of f, x and then conditioned on x and b to 0 to n, right? That is little x naught and that is little x naught. Right? So, we're good to go. The last equality is clear because if I tell you x of n is little x n, then that is just this. And that is already fixed.
Isn't it f of y comma n plus 2? Because we have the plus 1 in there.
Something wrong?
I don't know. We have the f.
So this sum here is n plus 1. That's going down n. Not n plus 2.
But up here we are plugging in n plus 1. So if we plug in n plus 1 in there, we get n plus 2 in the other side.
Okay, so maybe I'm running fast here. So what is this, right? Well, based on the definition of a conditional expectation, that is summation f evaluated at the little y and plus 1
Equal.
probability x n plus 1 is equal to little y, condition of x n is little x n. No? Yeah? Well, the value of this function f and tech multiplied with probability, I have that value. Of course, here the summation will be y in state space for sure. course, I will just rewrite this as the P. So that is summation F Y n plus 1 P x n 1 y minus and well, based on the definition of the function f, right? That series there is just f evaluated at x of n with the index being n. Based on that. Of course, this last piece here is simply so this last piece is simply well, for the sake of completeness, and mission number right. So okay. Kind of awkward, isn't it? Like if you have n plus 1, then you go back and it's got a little bit brain squeezing. But once you write down the Markov Markov property together with the P, then it shouldn't be too bad. Okay. So I'm gonna keep this example, all right? And move on to example 3. And now suppose I have a okay, what do I want to call? I want to call. I guess I want to go back to the example number 1. I guess let me call it to be say. Z IID, okay, with the IID with the probability this is equal to 1 or -1, again, Rubin. Okay, I forget the name. So that was supposed to be the Gamber Rubin. So considering ZM, right? So IID, the outcome for each game is equal to 1 probability P and a -1, 1 minus P. Right? And denote by Xn to be the sum of Zk. That is the total cash after n games. So I hope you guys still remember this is just a basically this is just a Markov chain. So it's a Markov chain. Okay. Now let me denote as F is 1 minus P. So the claim is that is the morning game. Respect to I just skip the condition 1 and 2. I just focus on the money game property. So condition on the past, I
how it's been. So, how do I invoke? So the trick here is actually,
Well, I mean, a couple of ways you can do this, but you can just employ example number 2. You can employ example 5.2. Oh, sorry, example number 2 there to see it.
so we not f x n minus b over b.
Alright. And so the claim is, I want to show this function f indeed satisfies that equation. Okay. So how you see it? So I have, so I will start with the series on the right hand side. Observe f summation of what? P x y. So that will be 1 minus p over p to the y minus. Okay. The first thing is, suppose my total cash is x, where I can go next in one step. Suppose I am at location x, where I can go next in the Markov chain.
F minus 1, F
Right. Only plus or minus 1. So this series here actually just comes down to p x plus 1, 1 minus p over p, x plus 1, plus p x minus 1, 1 minus p over p, x minus 1. But then this is just p, right? I win, so I go with probably p, 1 minus p over p, x plus 1. And then I lose here, that is what we need in 1 minus p times 1 minus p over p, x minus 1. And the sum here is indeed equal to, well, I guess I should do some, what can you pull out? So I would pull out 1 minus p over p to the x. Alright, pulling that out, I am left inside of the bracket. First term, that will remain 1 minus p. On the second term, that will be. Alright, and so that bracket is 1.